Hey there, calc folks. Back here with another quick video. I hope it's quick. I know the last two have been kind of long. This one I hope is a little shorter. I'm only going to spend just a little bit of time here looking at limits at infinity, folks. I don't want to, I'm not going to, this isn't going to be that drawn out. I promise on this set of notes. What is going to follow a little later on, we are going to see in a later video are some rules that are going to come back, a set of limit laws that we're going to rely upon to help us calculate limits at infinity a little further. But what I am trying to do here is just introduce you to the concept of a limit at infinity, right? And help you recall the college algebra skills that you're going to need to calculate these values and understand these values in a sense. All right, let me pull up the notes here. Here are the notes. All right, we're just looking at limits at infinity. And to begin with, I always point out you don't want to confuse limits at infinity with infinite limits. Right? They are two different cases for limits involving infinity. Infinite limits are the case where the dependent value of the function approaches positive or negative infinity in the limit calculation. Whereas a limit at infinity in the limit statement, in the limit calculation, it's the independent variable value that is approaching plus or minus infinity. All right? It's about what variable is heading to infinity in a functional relationship. Is it the independent or the dependent variable? If it's the dependent, it's an infinite limit. If it's the independent, it's a limit at infinity. And then just to make it that much more confusing, you can also have infinite limits at infinity, which is the case where both dependent and independent values in the functional relationship are approaching infinity in the limit calculation. All right? So, yes, it can be even that mixed up in a sense. But what we're trying to focus our attention on in this section is the idea of limits at infinity. And what we mean by that is a limit where the independent value, as we note here, is either approaching positive infinity or is approaching negative infinity. Where what we're describing, right, when we think about a limit at infinity, is we are getting into the idea of describing what we call the end behaviors of the graph. If we want to think about what's the limit as I head all the way down towards positive infinity for my x value, all the way down there, I'll be describing the right end behavior all the way down there for my function. Or similarly, if I'm interested in all the limits behavior all the way to the right, left, all the way down there towards negative infinity, I'd be interested in the function's left end behavior, right? Limits at infinity are interested in the end behaviors of the functional argument for a limit, right? The behaviors for the left and right ends, or what we would say are the tails in the graph, right? What does the graph do at its ends, right? What it does at its ends, or what does a function do at its ends, is a description of its end behavior, and end behavior is described with limits at infinity. All right, we can look at an example here. All right, we might consider, for example, the function f of x equals 3x divided by x minus 1. Right? And we might consider the right end behavior for this function. Well, in the case of right end behavior, we would be interested in the limit of this function as my value of x approaches positive infinity, right? As it heads all the way down there towards positive infinity. How does this function behave? How does the right end of this function behave? That would be this limit at infinity. Right? This is an example of a limit at infinity. These are pretty explicit in being able to recognize a limit at infinity. They will incorporate into their limit notation the independent variable of your function approaching infinity or negative infinity. Right? Now, we should have a little bit of understanding about how the right end of this graph behaves. Right? This is a rational function. Right? 3x over x minus 1. And as I substitute in larger and larger and larger values of x, right? As I head off towards positive infinity with the x values in this function, the numerator and denominator, right, behave in a way that has the dependent value of this function approaching the value of 3. Right? When we think about the argument inside here, as we get really close to infinity, it's almost as if we're calculating the quantity 3x divided by x, which would then just be the limit, right, as x approaches infinity for the simpler form, the value of just 3. Right? We could argue very quickly that that result of 3 could be potentially the result that we see in this answer. We do, however, have that minus 1 in there. Now, let me get it in there. Right? Where to draw that conclusion with that form could be a little bit hazier, right? A little harder to agree with. What we do have to go back to is that remember that this is all supported by asymptotic behavior. Right? The graph of 3x over x minus 1, when you go back to the college algebra, this rational function illustrates asymptotic behavior at the value of y equal to 3, or at the value of the dependent value equal to 3. This location right here in the graph, which we see illustrated here in the graph of this function. As x heads way down here to positive infinity, notice I already have it at 100, and it's already getting really, really close to the value of 3. And again, what we see being illustrated in behavior primarily is this limit, or this functional behavior for 3x over x. That minus 1 has very little impact, so that has us heading towards the value of 3. We can draw a lot of that conclusion about the horizontal asymptotes also, though, from the degrees of the numerator and denominator. Both the numerator and the denominator have polynomials of degree 1. That's a first degree polynomial. That's a first degree polynomial. And remember, in the case of a rational function whose polynomials in the numerator and denominator have the same degree, the end behavior is described by the ratio formed by the leading coefficients in the numerator and denominator. Right? Those leading coefficients are the value of 3 in the numerator and 1 in the denominator. So in terms of end behavior, we're heading towards the value of 3 over 1 along the y-axis, which is what we see going on also in this graph here. Right? That's all college algebra skills, right? This concept of end behavior. All right. Notice the same behavior for f of x equal to 3x divided by x minus 1 is observed for the left end's function's behavior. And that is illustrated by this limit at infinity, the limit as x heads to negative infinity. That's describing the behavior of the dependent value as we head towards this left end, down towards negative infinity. And similarly, for the same function, we see that it's equal to the value of 3. Now, I think we come back to that analysis here. But at this point, I do believe I bring up the definition for what a limit at infinity is, right? And for a function y equals f of x, the right end behavior, right, will be described by this limit, and the left end behavior will be described by this limit, where both of these limits are illustrating what we call limits at infinity. Right? And as we go on to further say, a limit at infinity describes the dependent variable behavior in a functional relationship as the independent value increases or decreases without bound. Limits at infinity are interested in the dependent variable's behavior as the independent value either increases without bound, as we see here in this example, or decreases without bound, as we see here in this example. Right? Both illustrating limits at infinity. Note a left-sided limit. Well, careful there. Note limits at infinity are also just cases of one-sided limits. This is known as a one-sided limit. Right? They're not going to be two-sided. You can only approach positive infinity from values smaller than it, and you can only approach negative infinity from values bigger than it. So in limits at infinity, they're always going to be considered one-sided limits, which means they should be able to be evaluated, and you should not be answering does not exist. Does not exist only is an occurrence that occurs for the value of a limit when the left and the right-hand side approaches don't exist. The case for a two-sided limit cannot exist. But these one-sided limits will always evaluate, right? They'll always have a value that you can find for them. You can't say they don't exist, right? And again, a left-sided limit is the case for describing a right-end behavior, and you have what's called a right-sided limit in the case for describing a left-end behavior. This is an example of a left side limit because you're approaching from the negative direction. This is known as a right-sided limit, right, or a right-hand limit because you're approaching from the positive direction. Right? We don't put on those superscripts because that's kind of implied by the infinity itself. Now, what do I say here? To evaluate a limit at infinity, it's often useful to understand the end behavior for your different types of functions that you studied back in college algebra. When you study college algebra, you study about all different types of functional behavior and learn how to perform functional analysis on a whole variety of functions. In that study, one of the aspects of the study is end behavior, describing how the ends of your graph behave. All right? We learn things like polynomial functions. The ends can do one of four things. They both could point up, or they both could point down, or they could point in opposite directions with either the left up and the right down, or the right up and the left down. Right? For rational functions, we learn that we can have horizontal asymptotic behavior that occurs along the x-axis, or occurs at some height along the vertical axis, or can even occur in an oblique manner, pending the degrees of the numerator and denominator. We understand exponential functions have an end behavior that begins very close to 0 on the left side and increases towards positive infinity on the right. All right? We have all these different understandings for different function types and their end behavior, and we have to use those understandings when starting to evaluate limits at infinity. Right? I do think I say here in the previous example, right? We understand from college algebra that we do have horizontal asymptotic behavior expected at the value of y equal to 3. It is expected at what we think of as the y value, where we have the ratio of the leading coefficients for the two polynomials that we find here in the numerator and denominator of the rational function. They both have the exact same degree, right? We just use the ratio of this leading coefficient to describe the end behavior. And that's where we obtain the results that we saw above for this limit at infinity for that function and limit at negative infinity for that function. Let's look at another example. You might consider the limit as x heads to negative infinity for the statement 4 over 2x plus 7. That's also a limit at infinity for this rational function. But unlike the previous example, right? But unlike the previous example that had the same degree in the numerator and denominator, in this rational function, we have a constant value in the numerator, a 0-degree polynomial, and in the denominator, we have a first-degree polynomial, a linear function. Well, what happens when we divide a constant by a linear, right? The values for the output of that function, as we head towards negative infinity, is that the outputs for that function get smaller and smaller and smaller. And what they do is they approach the value of 0. Taking a number like 4, right? Taking a number like 4 and dividing it by something that gets really close to infinity. So if we think about this 2x plus 7 down here, it's actually going to send itself off to infinity. Whereas the numerator, right, is going to, in a sense, be sending itself still to the value of 4. Well, when you take a constant and you think about it being divided up into a value that's heading to infinity, each of those divisions is getting smaller and smaller and smaller as we get closer and closer to infinity, to the point where the dependent value of this function, the value 4 over 2x plus 7, is going to get really close to the value of 0 as you head to either plus or minus infinity. If you remember back to college algebra, because the degree of the numerator is less than that of the denominator, we have horizontal asymptotic behavior expected at y equal to 0, or along the x-axis in the graph. So we can conclude this about our limit at negative infinity. Now, all of this is supported by the graph, if we bring that into view. Right? Again, this is supported graphically, and there's your graph. Notice as we get closer and closer and closer to negative infinity down here, that function is getting closer and closer to 0. It's a little less than 0. It's always going to be a negative value, a little less than 0, but it's going to get closer and closer to 0 as we move further and further and further to the left along this graph. Right? Again, it's understanding the end behavior of this function, right? That's going to allow me to evaluate this limit at infinity. Limits at infinity describe end behavior. This particular case describes the left end's behavior. All right? Let's do, I think, one more here is what I have. Yeah, lastly, consider the right end behavior of this polynomial. All right? Well, the right end behavior of this polynomial is going to be described by this limit at infinity for that polynomial. All right? That's going to describe the values way down there at the right end. Right? So if we think about the end behavior of a polynomial, if you remember, we could have one of four behaviors. They both could point up, or they both could point down, or they could alternate pointing up and down, where the left or the right is pointing up and the other side is pointing down. Now remember how we figured that out from college algebra? It all involves analyzing this very first term, negative x cubed. How does negative x cubed, how does its ends behave? Because the ends for this polynomial are going to resemble the ends of the power function negative x cubed. And negative x, well, first of all, x cubed is going to have the two ends point in opposite direction. All right? Actually, that would be like this. The left end would point down, the right end would point up. Right? And then when you take the opposite of that with the negative out in front, that behavior switches, reflects. And the right end points down now and the left end points up. In the graph of negative x cubed, the right end will point down and the left end will point up. So the end behavior on the right end will be heading down to negative infinity. And what we end up seeing is an example of an infinite limit at infinity. Right? Again, in this case, f defines a polynomial. And polynomials have an end behavior that look a lot like the power function that resembles the leading coefficient for your polynomial. And negative x cubed we should be familiar with as a power function, right? It's the case where your right end points down and your left end points up, right? And it's that cubed shaped graph, right? So the limit as we head to the right in that end behavior is going to have us heading down towards negative infinity. And what this becomes an example of, as I had noted at the beginning here, is what's called an infinite limit at infinity. All right? It's an infinite limit because the independent variable x is heading to infinity, and we are interested in the right end behavior. It's an infinite limit. That's a limit at infinity. It's an infinite limit because the dependent value is approaching an infinite result. It's approaching negative infinity. Right? I do think I also support this graphically. If you take a look at the graph here, right? No, these results for limits at infinity are supported by the following illustration. Here's the graph of that polynomial zoomed out to a considerable degree to show you that when you head to this right end, as x heads to infinity, as it heads off to this right end, even getting close to about 50, not even out to 100, we can already see the dependent value is way down here at negative 100,000. It's approaching negative infinity in value. It's approaching this infinite limit. All right. I do think I make a conclusion statement here. Let's bring that up. Yeah. So I had opened with a set of rules will be presented at the end of this study for evaluating limits. I have a few more things I want to mention before I just give you a bunch of rules. But I am going to give you some rules that are also going to apply for the cases for limits at infinity. And with all the rules I give you at the end, including those with limits at infinity, you're going to have a pretty good foundation to build on your limit calculations. Right? That is my hope here, folks. I will tell you, though, that some of this foundation that you're building your limit calculations on, if you haven't figured it out, require those functional analysis skills that you developed in college algebra. To be good at evaluating limits requires superior functional analysis skills. You have to understand the different aspects for the different types of functions that we can study in mathematics. And here in limits at infinity, what we're interested in is the end behavior for these function types. So you're going to always want to know a little bit about end behavior to help you get through all of this. All right, to help you calculate limits at infinity. I'm going to stop there because, like I said, I want to try to keep this video short, and I've succeeded. We're just at a little over 25 minutes. What I am going to come back and look at, I think I have to talk about indeterminate forms. You had mentioned some of that in class already, and perhaps in these notes. I think I remember saying something about indeterminate forms. But I'm going to come back and talk about indeterminate forms just briefly. That's also going to be a short lecture set. And then, like I said, I want to get into those rules. I think that's what's going to follow. And at that point, we'll be have a collection of what we call limit rules or laws that we can also use to help in our evaluation process. That's where we're at, folks. So I'm going to stop there, and I will see you in class and in the next video. So have a good night, and I'll see you next time.